So good morning, class. So let's start with modern physics. Okay, this would be the first chapter of modern physics. That is dual nature of matter and radiation. Okay. So let's start. Dual nature, I would just write. Okay. So, before we actually start the topic, I would list down a few topics because the questions had been asked not from the core topic but from sideways things as well. Just like some questions had been asked from experiments. The Davis-Germer experiment you might have heard, right? So I'll take up from where we left off, the Hertz experiment. Yesterday we were doing Hertz experiment. When Hertz was performing his experiment, if you remember the diagram, there was something like this. These were two spheres, right? Other arrangement was also there. Some induction coil thing was there, right? This connection was made to induction coil, while here it was detector. Okay, here it was detector, right? So if you do remember, sparks used to jump across the two spheres from S1 to S2, or maybe from S2 to S1, doesn't matter, right? Sparks used to jump. So what Hertz observed, okay, I'll write Hertz observation. He detected that there are EM waves of frequency 1 by 2 pi under root LC. Okay? There were EM waves of frequency 1 by 2 pi under root LC. Okay? But what else he discovered, which was not mentioned in the yesterday's class, was that if these two metallic spheres were incident with UV rays, the sparks were even stronger. Okay? Okay, the sparks were even stronger. So if S1 and S2 was, this is frequency of EM waves were incident with UV rays, sparks were produced earlier, which means actually at lesser voltage. Okay, at lesser voltage, and were stronger, right? And were stronger. So what he concluded from this, that actually UV might be helping in releasing electrons from the spheres. Okay, in helping in pushing the electrons out of the spheres. Okay, so what actually was happening? You getting the point, right? Okay, so EM waves were more easily produced if there was UV rays already present in the system, right? So this observation, obviously the frequency was still same, but this observation, this directed people into another another format, into another investigation actually. So while the investigation for EM waves was complete, another form of investigation was unfolded, that how actually UV radiations help ejection of electrons. Okay, so we would be studying that only. That's called photoelectric effect. So I hope this is clear. Okay, the questions had been asked even on this actually, observation, only on the observation thing, right? So I'll erase this. So before we start the actual topic of photoelectric effect, Okay, I'll write this thing, work function. What is work function? What is work function? Hmm. Hmm. The minimum energy required for ejection of electrons from a metal surface, right? And the symbol is phi naught. Okay, symbol is phi naught. Just a second. Right? Okay, so basically electrons get ejected from metal surface if you provide some energy. Now that energy can be provided in the form of in multiple forms. So the way, on the basis of the way of providing energy, we have different names for the procedure. Okay, so types of ejection. First is thermionic, which is due to heat. Okay, you heat a metal, it ejects electrons, and heating means like really high temperature. Okay, okay, then field. This is you apply very strong electric field or very high potential, whatever may be the case. It means the same thing. So this is due to strong electric field. Third, secondary. What is secondary? You know, when fast moving electrons strike a metal, they actually cause emission of electrons of the atoms. Something like this. Let's say this is atom, this is an electron, and you have a fast moving electron. It strikes, and finally you get two electrons. Two electrons exit, and lot of energy is released. Okay, so now this is due to fast moving electrons or high energy electrons. And last but not the least, we have photoelectric effect, right? Fourth is photoelectric effect. Okay, so it is when light of frequency more than a particular frequency is incident on a metal, electrons are ejected. This phenomena okay, so total textbookish definition, right? This phenomenon is called photoelectric effect. देखिए थर्मियोनिक सबके लिए होता भी नहीं है, ठीक है, लेकिन टेम्परेचर जनरली काफी हाई होता है. इट इज लाइक मोर देन मेल्टिंग पॉइंट ऑफ द मेटल इटसेल्फ, राइट? Okay, so now you would be studying photoelectric effect, right? Can I erase this? कर दूं erase तो ये तो it's like definition only, you know this. Hallmark's and Lenard's observation. What was it? You know, they gave the actual experimental setup of photoelectric effect. It was this. This is what? This is the variable battery. Okay, you can change the voltage as well as the polarity. Okay, actually this arrangement is made using a commutator. You know, you switch the terminals. Okay, so all this, you know, you need not understand what actually is happening behind the scenes. We just say it's a variable battery and we can vary the potential difference, right? Variable EMF source, while G is the galvanometer, right? Okay, this is cathode and this is anode. The cathode is actually a photoelectric metal, right? What was their observation? That when light of certain wavelength, light below certain wavelength or above certain frequency, in whatever way you can think of, okay, when light of certain frequency, above certain frequency is incident on the metal, okay, electrons are ejected. So you observe some current. Let's call it microammeter. It is highly sensitive, okay, because the current would be in micrometers, microamperes, right? So electrons are ejected and there is some current in the circuit. Okay, the ejected electrons are called photoelectrons. Okay, the current is called photoelectric current. Is it okay? Right? This you already might be knowing. Okay, this you already might be knowing. So this was their experimental setup on which some observations were made. Okay, so let's study. This is a simplified form. We need not understand how the battery was reversed or something. Okay, so please draw it. Shall we start? Okay, so the observations were this. First one, the effect of frequency. Okay, I would be writing a very shorthand format, okay, so that it doesn't become cumbersome. So it said if frequency was more than the minimum frequency, what is the minimum frequency called? Threshold frequency, right? Okay, so we would be using the term threshold frequency, TH. So if frequency was more than or equal to threshold frequency, photoelectric effect happened, okay, but if frequency was less than threshold frequency, no photoelectric effect even if intensity is high. It means if the light has if the light has less frequency, whatever may be the strength or intensity of the light, doesn't matter. Photoelectric effect nahi hoga. It won't happen. Okay, this was the effect of frequency. Can I erase this? Okay, I would write everything in this shorthand format. So the second effect of intensity. Okay, the condition here was that frequency was already right. The condition was this: frequency was already more than threshold frequency, right? Because if it is lower than threshold frequency, photoelectric effect won't happen at all. If frequency was above threshold frequency, which means already photoelectric effect was happening, then the photocurrent IP, I'll draw it, show it here. Photocurrent is IP, is directly proportional to intensity, right? Is directly proportional to intensity, with the condition that frequency is higher, which means graphically if I plot IP versus intensity, it's a straight line graph. Is it okay? More the intensity, more is the photocurrent with the given condition, right? दिख रहा है आपको? Okay, shall I erase this? Effect of potential or voltage. So what they observed, that let us assume initially the potential was 0. Initially the potential difference was 0, voltage was 0, which means the EMF source was switched off. It was acting like a wire. Is it okay? Okay, it doesn't mean कि connection open हो गया. It doesn't mean connection is open. It simply means that the battery is switched off. It's behaving like a wire. Okay. Okay. So in this scenario, what happened when the light was incident? Again, the condition. What is the condition? No, frequency condition should always be there. It should always be there, right? Okay. Again, with the condition that photoelectric effect may happen. So in this case, as let's say initially when V was 0, there was some photocurrent. As voltage was increased, photocurrent increased. Okay, But at one point of time, what happened? Saturation, at one point of time, saturation happened. Is it okay? Okay, so any further increase in voltage couldn't increase the current, right? As V increases, IP increases, but up to a limit. That limit is called saturation current. Okay, this was part 1 of this effect. Part 2 of this effect would be, shall I increase? Oh, shall I erase? Sorry. Shall I erase? Now the part 2 was this. If V is less than 0, V becomes negative. Okay, what's happening? If voltage is reduced, what's happening? The photocurrent stops, reduces and stops at a voltage called stopping potential. Okay, IP reduces and stops at a voltage which is called stopping potential, Vs. Okay, if it's okay, I can draw the graph. The graph is this. Yes. It's not time, it's potential. You keep on increasing potential, the current would become saturated. Explanation aayega. Hold. These are just only the observations. Okay. So when voltage was 0, there was some saturation, some photocurrent. If you increased the voltage, current increased, but up to a limit, after which saturation came. Okay. So saturation means the graph should become parallel to the x-axis. The value is not increasing now. If you decreased the potential, the photocurrent reduced and became 0 at some point. This is minus Vs, the stopping potential. Okay. Okay, this was third one actually, sorry. Okay, third one in which we had 2 possible observations. Is it okay? Right? Right? There is one more, actually, some more additional observations were there. Okay, some more additional observations were there. These were the 3 primary observations. The other observations were these. Okay, I would write the 4th observation was, if a light of more frequency is incident, then stopping potential is more. If a light of higher frequency is incident, stopping potential is more. So the graph for IP versus V has another addition to it. What's the addition? Now this is for frequency F1, Okay. This is minus Vs1. This is the graph for minus. This is the graph for frequency f2. Okay. This is the graph for frequency f1. Okay. We are assuming that the intensity is same, because if intensity had been different, what do you think? If intensity had been different, then obviously the photocurrent would have been different as well. Okay. So we can add that as well, but in a separate graph I would draw it. Okay. So here I1 is equal to I2, right? Shall I erase this? Fifth would be if intensity of light is increased through some factor saturation current increases by same factor. So what it simply means? It means that let's say this is photocurrent, this is VA, right? This is minus Vs. For intensity I, let's say this is the graph. The saturation current is something. Sorry. Now, what happens? For intensity 2I, the graph is exactly double. Saturation current is exactly double, right? Okay. Here, since stopping potential is same, the frequency is same. The frequency is same. Is it okay? Is the idea clear? So, a question which came, a lot of years back, which is, these days it is asked in your school exams. This is the question. Is it done? Just finish it, then we would do that question. Correct? The question is this. Okay, these are 4 graphs. This is A, this is B, this is C, and this is D. Okay, you have to pick pairs which have same frequency and pairs which have same intensity. Pairs of same frequency, first part, pairs of same intensity. Tell me. AB, A and B have same frequency, while C and D also have same frequency. Okay, and for same intensity, A and C have same intensity because they give same saturation current. B and D have same saturation current, same intensity, right? Shall I raise it? I raised it already, right? Yes. Yeah, I erased it. ये किसी को लिखना तो नहीं था. It's like very easy. Okay, right? So now the last observation. We till now we noted how many? 5 observations. The 6th is actually a very easy, not very significant observation, which is there is no time lag. The moment light is incident, what happens? Electrons come out, right? They are rejected. So there is no time lag. Now let's discuss the explanation. First, wave theory. People who support wave theory, they try to explain it. You understand Huygens wave theory? You remember, right? So Huygens wave theory. People who support Huygens wave theory, they explained it. In Huygens wave theory, now there is some addition because of the work of Maxwell. Okay, we studied EM waves. Huygens gave his wave theory way back, but Maxwell had some addition to it in the form of energy, electric field, magnetic field combination, and so on, right? So on that basis, it was explanation was tried that actually when light falls, okay, what happens? The metal ions, they absorb electrons, they absorb energy, and electrons are ejected. But there was a problem in this. There were actually a lot of problems in this model. Okay, the problems in wave model were actually, first of all, let's say intensity of light is very low. Okay, so wave model says that if intensity is very low, photoelectric effect should not happen, right? Because very low energy. But instead we observed that even if intensity is very low and the frequency is suitable, okay, photoelectric effect was happening. Then wave theory said that if we increase intensity to very high value, lot of energy incident on the metal, so what happens? Photoelectric effect should happen, right? But again, it was not happening. If frequency was lower than the threshold, no photoelectric effect. Okay. However, maybe the whatever may be the intensity, even if intensity is very high, photoelectric effect was not happening, right? Third, according to wave theory, you can understand this, that when light is incident on a metal, it's not suddenly that the atoms acquire energy and eject electrons. Okay, there is some time delay. For normal these lights, the time delay may be as much as 10 hours. Okay, for these room lights, if you try to go through photoelectric, try to perform photoelectric effect with the help of these lights, then this wave theory says that it may take up to 10 hours. But you understand this, that it takes only few seconds, even not even few seconds, it takes fraction, 10 raised to minus 8 seconds type of time. The light falls and electrons are ejected. Okay, so there is no time lag. So it couldn't explain anything, so that's why it was rejected. Okay, and then somebody thought about the particle nature of light. Who was that guy? Planck. Planck's quantum theory. What it says? You have studied this in chemistry. What? अरे theory. What is the theory? Statement कुछ याद हो? Huh? Light exists in the form of actually everything in the universe. He postulated that even matter, physical quantities, okay, matter, physical quantities, radiation, everything exists in the form of small packets. Okay, it's called quanta, and quanta for light is photon. So for photon, for light we would say that light exists in the form of small quanta, small packets of energy called quanta, and the quanta for light is photon. So he said that for light the energy of one quanta is given by this. Okay, this is the energy of one quanta. Okay, please note Hc can be written as 12400 angstrom by lambda. Okay, it is instead eV angstrom, sorry. Okay, this comes very handy when you solve questions. So Hc is actually 12400 electron volt angstrom. If you place lambda in angstrom, if you place lambda in angstrom, you get energy in electron volt. This is the energy of one photon. Is it okay? And light, as you know, is made up of a lot of photons. So this would be right. We discussed this yesterday. Shall we continue? Okay. So on this basis, some explanation was given. Okay. Okay. Who was the guy? Einstein. Explanation. Let's check. Okay, we won't be writing a lot about it. Just hear me out so that all your questions are answered. Okay, we would be handling only his equation, Einstein's equation, right? So what Einstein said, actually, you know, Einstein was given Nobel Prize for this and not for theory of relativity. People think that he was given Nobel Prize for theory of relativity, right? He did so much work, relativity, ये वो speed of light से travel कर सकते हैं and all, right? Okay, there's a misconception. Okay, he was awarded Nobel Prize for the explanation of photoelectric effect. Okay, which like to you it would appear कि कितनी easy चीज थी इसके लिए Nobel Prize, but it was one of those puzzling problems of physics in those days. right? So he explained it, and it took him like a lot of time, 19 years or maybe 16 years, experimentation and all, right? So let's study. What Einstein assumed was that light incident on the metal is actually in the form of photons. Okay, light has a dual nature. Okay, it can behave as a wave as well as a packet. The wave nature comes in picture when you are interacting with larger sized you can say obstacles, right? While the particle picture comes in particle nature comes in picture when you are dealing with electrons. Is it okay? So he said that light behaves as a wave as well as an electron, as a particle, sorry, but the particles interact with electrons. Okay, it is the particle nature of light which we would be using here. So he assumed particle nature. Of light. Now how he explained it? Now for that explanation, just assume that for an explanation, let's assume, you know, we need to join all the points starting from the work function till last point of photoelectric effect. So for that understanding, आप ऐसा समझो. Let's imagine you have a town in a desert, right? You have a town in a desert, okay, with some water supply. Let's say you have huge amount of water supply for you, Dubai, right? Okay. अब आप मुझे बताइए, just tell me one thing. When you are in a desert safari, let's say you are in a desert safari, you have 2 bottles of water. Some thieves come and try to snatch one of your bottles. Would you allow them to take your bottle? Desert में, right? Definitely not. Desert की बात छोड़ो, तो यहाँ पे भी नहीं करने देंगे हम, right? Idea समझ आया? आप desert safari में हैं and some people come to snatch your water bottles. Would you allow them? Definitely not. Okay? A lot of energy is needed on their part to remove your bottle. For isolated atom, for, you know what is isolated atom? Gaseous isolated atom, right? For isolated gaseous atom, these atoms are their water bottles. You are trying to snatch water bottle from the poor guy. So he would retaliate a lot. You need a lot of energy. That's called ionization energy. Understand the idea? Ionization energy is the energy needed to remove one electron from outermost shell of a single gaseous isolated atom, right? Now, in case of a metal lattice is not isolated, it's not gaseous, okay? They all are joined together. And in case of metal lattice, you know, the electrons, they don't actually, you can understand this in this manner, they are like free. You understand the word electron C model? Solids में कुछ पढ़ा है? Huh? Electron C model. What this model says that actually in case of a lattice, the metal atoms form ions, okay, and form a regular arrangement. The electrons are free, the outer electrons are free to move everywhere, okay. So they flow like a sea of electrons. That's called the electron C model. ऐसा कुछ पढ़ा होगा? You might have heard. You know, without this model, you cannot explain the concept of resistivity, conductivity. Chapter 3, remember? Current electricity. So this is the model you actually know right now. Pata hai. Maybe you don't know the name. It's called electron C model. So now in case of a electron C, of a metal lattice, you have so many atoms. Everyone contributes his valence electrons to the pool. So you have a common pool of electrons, and from that pool nobody can recognize कि ये मेरा वाला electron है, मुझे दे दो, right? Nobody can be selfish now, okay, right? From that pool all of the electrons are like similar, okay, ठीक है? What if now somebody tries to remove 1 electron, उतना दुख नहीं होगा ना. Compare the two situations. Single isolated gaseous atom, you try to remove 1 electron, you require a lot of energy. You have a lattice here. In the lattice, you have so many electrons, billions, trillions of electrons. If you remove 1 electron, it won't be that difficult now, right? Why? Because even if you are a desert town, and you have a water supply, limited water supply, but that water supply belongs to all of the people. It's huge. The water supply is huge. So even if somebody steals one bottle, you would rather allow, ठीक है, okay, हो गया, right? This is for, work function for you. Work function is very small compared to the ionization energy. Why? Because here you have a pool of electrons. Removing 1 electron is not a big deal. Okay, but what happens when you remove 1 electron from the pool? Okay, the surface acquires a positive charge. Okay, so you need to have sufficient enough energy to remove it away. If the energy is insufficient, it is held back. Okay, चलो रहने दो, बोतल भी नहीं लेके जाने दिया आपने. 1 bottle water. हाँ, अभी तो बताया. Ionization energy is for 1 atom, while work function is for a lattice. So in ionization energy case, you are removing the electron from the orbit, outermost shell, while in case of work function, you are removing it from the common pool. They are no longer in the shell. They are free to move. So you are removing 1 free electron. Removing 1 free electron takes a lot less energy, 1000 times less even, right? Okay, so shall I continue? है ना? So what he explained now, this was the difference between ionization energy and work function. Okay, so obviously with light you cannot ionize an atom. It's not easy. It's you need discharge and all, so many things, but it's easy to produce photoelectric effect for a lattice, right? So what he said, let's understand this. He said that actually the light is in the form of small packets. Every packet enters into the lattice. Okay, every packet enters into the lattice and an electron receives the packet. If the energy is sufficiently high, the electron will eject out. But let's please listen to this, that not all the electrons who receive the packet are lucky enough to go. What happens? Let's say there are so many directions in which an electron can go. So when an electron receives a packet, its kinetic energy increases, it suddenly rushes, right? So what happens if it is not coming out of the surface? It may go in some random direction. It may have a collision with another electron. So in that case, its energy is shared. If the energy is greater than the work function, it won't be able to come out. In other case, it may go inward as well, right? Getting the point? Let's say here is the electron. Okay, I would mark it star. Star means that this has this is at higher energy state. Already it has received a photon. So if it comes in this direction, it is able to come out. If it goes like this, so many possible directions in which it won't be able to come out, right? So only 1% of the possible photoelectrons come out. If 100 photons fall, then only 1%, only 1 electron would actually come out. That's the ratio generally, even lesser, right? So now a thing comes into mind that ऐसा नहीं हो सकता that electron gathers energy, loses some of it, then once again it gathers energy and comes out. So the idea for that is an electron cannot gain, absorb 1 photon unless it has lost all of the energy of the photon. So So electron is like a one pocketed guy who can only handle one bottle. Is it okay? Okay, who can only handle one bottle. So till the time his bottle is empty, he cannot put one more bottle in the pocket. It's like that. Till the time whole of the energy of the photon is not spent, he cannot absorb another photon. So the model for this, I would explain this on the basis of a prism model, jail model. Okay, the prism model. What happens? Let's say the lattice, you have a lattice. Lattice is kind of like jail, okay, a prison, in which the prisoners are the electrons. No prisoner can escape out, because if somebody tries to cross, the lattice pulls the prisoner back. Is it okay? Okay, this is the arrangement. So now what happens when photons are incident? When photons are incident, okay, so photons are like, you can say 10 rupees ki rishwat. Okay, so now you have some rishwat. The prisoners, they have some rishwat. Okay, it's raining 10 rupee notes. The prisoner can pick one note, put it in the pocket. Okay, and let's say the gate pass is for rupees 5. So what happens? He gets 5 rupees extra and he can leave. He spends 5 and he can leave, right? Is it okay? Now let's try to understand more about this model. Getting the model? Getting the model? The prisoners here have only one pocket. They can place the rupee, the money collected from by picking up the note in that one pocket only. Okay, until unless they have spent all the 10 rupee, whole of the 10 rupee, they cannot leave. They cannot pick another note basically. Okay, ठीक है? So now understand this model. So model में क्या है कि अब what happens? ऊपर से 10 rupee notes are raining. Okay, a prisoner would pick 10 rupee. He would try to go to the gate, give 5 rupees and leave, right? But not all would be that much lucky. Okay, what happens? One prisoner is going toward the gate, another is running, they collide, they lose their money. That happens. Electrons collide, lose their energy. Okay, both of them cannot come out. Another thing happens, that say you collected 10 rupee, you have a guard in between. Now that guard asks, कहाँ जा रहे हो? गेट की तरफ जा रहे हो? पैसे आए होंगे, मेरा cut. So that guard asks for his cut. You lose 2 rupees, still you have enough to go out and survive, right? Okay, so this kind of thing happens. Now let's imagine what could have been a typical scenario. Some prisoners would have been really lucky. They receive 10 rupee, okay, they go to the gate, they get 5 rupee in return, they leave. The best guys, the luckiest guys. Some are less lucky, right? They pick 10 rupee, again same photon energy, but they collide with the guard, they lose some money, okay, they lose some energy, still they have enough energy to come out, they leave, right? Okay, some other guys, they pick again 10 rupee, but they lose 5 rupee in the process. They met 2 guards, let's say, or 3 guards, right? They met 3 guards who took some money. They only have 5 rupee. Now they are just able to exit, right, with 0 energy. So you understand that? Understand this? The prisoners, okay, the richness of prisoners is in a range from 0 to some maximum value. So similarly, the electrons have energy in a range from 0 to, let's say, K max, the maximum kinetic energy. The maximum kinetic energy is what? The energy supplied by a photon is nothing but hc by lambda. Out of this, the work function is spent and the rest of all they carry. Getting my point? The 10 rupee note, 5 rupee gate pass charge, they carry 5 rupee out, right? all others are not so lucky, so their kinetic energy would be lesser than the maximum kinetic energy. Kinetic energies are in this range. Is it okay? So understand this. I guess the point is clear. Okay. The points worth noticing was that that light falls on the metal in the form of packets called photons. Okay. So light is in the form of photons. Electrons absorb most of the photons, actually go waste. They don't fall on electrons, they fall on metal ions, which are huge, have very large mass. So that much amount of energy won't help them in any case. So most of the photons go waste, few photons fall on electrons. Okay. So out of those few electrons which receive energy, very few are lucky enough to come out, who are headed in the upward direction statistically. Otherwise some would go in this direction or that direction, would collide, lose some energy. So some can still come out, while others would still remain in, they would keep on colliding, lose their energy. Okay, come to the normal state. Okay, until unless they come to the normal state, they are, they cannot receive further photons, right? That's the whole scenario. That's what Einstein explained. So somebody asked what happens to the electrons which just exit the surface with no energy left. When an electron is ejected with no energy left, it just stays out of the surface. It stops. Okay, it stops after some distance when the effect of positive charge on this is not felt by the electron. It just stops, loses all the energy. बीच में रह जाता है. हाँ अभी हम लोग एनोड क्या कर रहा होगा अभी हम सोच रहे हैं, बट हाँ इट वुड, यहाँ पे zero energy electrons would form a cluster somewhere here. It is very small amount of positive charge, plus E is very small amount of positive charge, right? Okay. They move up to a point where there is no attraction. So ऐसे तो तुम कहोगे कि ऐसे तो attraction infinite तक होता, but because of one electron, how much would be the attraction, right? That one plus E charge is even spread on whole of the plate. How much is plus E charge for whole of the plate? It's negligible. So we assume that when an electron comes, it comes out of the surface up to some distance. Okay, it comes out of the surface up to some distance. We assume that there is no attraction. Further energy absorb karega? This electron? No, this won't. मेटल सरफेस से आ रहा है इलेक्ट्रॉन, अच्छा नीचे से आ रहा है. हाँ ये ऐसे तो हो सकता है, मतलब आई थॉट दैट यू आर सेइंग दैट वुड इट एब्जॉर्ब एनर्जी फ्रॉम द इनकमिंग फोटॉन्स. दैट्स स्टैटिस्टिकली like really impossible. That's statistically really impossible. Okay, hardly 1% of the photons are absorbed. Then further 1% are the lucky ones who actually exit. So try to understand, statistically it would be 1 in a 10,000 type of chance, or maybe even more. So like very low chances of some photon striking this electron. Somebody, will it be suspended in air? Yes, exactly, somewhere in the region. And what happens to the electron? Means won't it get attached to any other surface? It may get. For ejection of one electron, only one photon is required. In fact, one electron one electron can absorb only one photon, that's it. By the time it loses whole of the energy of one photon, okay, by the time it loses whole energy, energy of whole of the photon, it is unable to receive another photon, right? जब तक एक पूरा खर्च नहीं हो जाएगा दूसरा नहीं मिलेगा. It's how pocket money theorem happens. Pocket money thing, you get a pocket money, आप पूरा खर्च करते हो, then you have to give हिसाब कितना कहाँ खर्च हुआ, right? ऐसा ही होता है शायद, मेरे घर में ऐसे ही होता था. Shall we continue? Okay, so you get the idea? You get the idea? Alright. Shall I erase this? Okay, so the final equation, yes, what happened? अच्छा ये तो हो गया ना, हाँ सब हो गए. On what factors kinetic energy of electron depends? The kinetic energy of electron depends on only one factor, the energy of photon. That's it. Work function we assume is fixed, right? Okay. So the range of kinetic energy is 0 to k E max. Okay. Just imagine ना क्या हुआ होगा. The best case is what? The best case. Electron receives photon, heads to the surface, okay, spends some energy while exiting the surface and keeps the remaining energy, right? So it receives hc by lambda energy, goes to the surface, spends work function, this is the remaining energy, this is the Einstein photoelectric equation, right? Okay. Okay. Okay, so you understand the model. Let's now get the explanation of each of the observations. Okay, let's now get the explanation of each of the observations. First observation was, if the frequency is lesser than threshold, no photoelectric effect, right? What it simply means is that, what? It simply means that if the photon has insufficient energy, then work function, then electrons cannot come out, right? It's like कि अगर in the prison, in the jail, what's happening? 4 rupee या let's say 2 rupee notes are raining. कुछ use है, 2 rupee उठाओगे, gate पे जाओगे और वो कहेगा sorry, rejected, application rejected, right? Of no use. Okay. So only if the amount of money falling is more than 5, the value of note is more than 5, only then the prisoners would be able to leave, because they have only one pocket. ऐसा नहीं होगा कि दो की 3 नोट उठाए और जेब में रखे. The electron can absorb only one photon. It cannot absorb 2 or 3 photons so that it is able to escape out of the surface. बताओ? They are photon. One note is equal to one photon, right? So the second was how much? What was the second thing? Intensity? Effect of voltage? Effect of intensity. Yeah, it was effect of intensity. More the intensity, more is the photocurrent. Now think about it. More intensity means more number of photons falling. More electrons would be able to take up would be able to absorb the photons, and more would be able to eject, right? It's easy to understand. Third one is potential. Okay, now let's try to understand the role of potential. What happens actually? Let's say initially the voltage was 0. Okay, initially the voltage was 0. Now the electrons are ejected, and it's not necessary that they would go straight. What happens? Because they can go in any random direction. Some would go here, some would go here. Very few would actually go straight. Okay? Okay? So these few would actually represent the photocurrent, right? as you make the battery positive, okay, which means this is negative, this is positive, this positive attracts those electrons which are hitting the glass tube, which are deviated through small angles. So it would actually absorb this in, even this in. The current increases. If you increase the voltage more, it would be able to absorb even this one and even this one. More current, right? But if you keep on increasing the voltage, what happens? What happens? Saturation, why it comes? Because there are some electrons which are here, which sit here without any energy. So when you increase the voltage, a time would come when even they would get attracted. Okay, so all the electrons from 0 to maximum kinetic energy are actually absorbed by the anode, are pulled by the anode. Okay, so all of the electrons now represent the photocurrent. Is it okay? Now if you if you increase the voltage, nothing would happen. You cannot get more electrons, more current. For more current you need more electrons, but by increasing voltage, photoelectric effect won't increase. It's just that all the electrons which were going here and there, stray electrons, were being pulled. Now with the increase in voltage, all the stray electrons were pulled. Okay, now since all the electrons are going into the anode, what happens? No further addition of electrons happens if you increase the voltage. Okay, you cannot get more electrons, so current is constant. You can increase the current only and only if, what happens? You can increase the current only and only if you increase the intensity on the cathode. Okay, intensity, not frequency. Amount of photocurrent is not dependent on frequency. फिर से करते हैं, कोई दिक्कत नहीं. This is a point where a lot of people get confused. Okay, so getting the point, ये समझ आया? आप voltage बढ़ाते हैं, you increase the voltage. What happens? More and more electrons which are going into the hitting the glass tube, more and more electrons are getting attracted toward the anode, है ना? So more and more current. But a time would come when all the electrons would be coming to the anode. When all the electrons are coming to the anode, you increase the voltage further, no effect. Jitne the 100 electrons were produced, all 100 are coming. No extra electrons, so no extra current. So that's why the saturation thing. Now to increase the current, you have to increase the number of photons. To increase the number of electrons, you have to increase the number of photons. Getting the idea? Okay, okay, more photons matlab more electrons ejected means more photocurrent. To increase the number of photons, you need to increase intensity. Okay, intensity. It's not the frequency of photon or the energy of single photon which matters. It's the collective energy, the number of photons which are coming, more number of packets. Is it okay? Right? Okay. However, frequency increase से भी there is some effect. What happens? Negative side हम लोग समझते हैं. Let's say we reverse the voltage. So now this one is positive and this one is negative. Okay. This one is positive and this one is negative. Now try to understand this. What happens? Now if this is positive, this is negative. Let's say earlier some electrons were going here and there, some were approaching like this. Okay, because of this negative charge, the reverse, because of the opposite electric force, the slow electrons coming in this direction would be repelled back. Jao tum wapas. When you increase the voltage, when you make the voltage more negative, even the medium energy electrons would be repelled back. Tum bhi jao. And as you make voltage more and more negative, the fastest electrons which means the electrons which represent this energy would be repelled back. Tum bhi jao, right? Getting the point? Okay. As you make the voltage more and more negative, so the faster electrons would be repelled back. At one point, even the fastest electron would be repelled back. Jao. Is it okay? At that time, the work done, the potential difference between these 2 points is Vs. The work done on the electron would be EVs. You remember the work done was QV. So the work done in stopping the electron is EVs. And by work energy principle, work done is equal to change in kinetic energy, right? Work done is negative, and so is the change in kinetic energy, right? So instead of Ke max, I can replace EVs is equal to Hc by lambda minus phi naught. This is another form of the photoelectric equation. Is it okay? Okay. Further more observations were there, that higher the frequency, more is the stopping potential. You can imagine, if the frequency is higher, the energy of photon is more. Okay. Now just imagine that in the prison now, let's say 20 rupee notes start raining. Okay. Now a prisoner has to spend only 5 rupees. He would be richer. 15 rupee leke jayega. To stop this prisoner, you need to apply even higher stopping potential. Getting the idea? Okay. That if high frequency photons are incident on the metal, what happens? Electrons come out with even higher energy, and to stop them you need even higher stopping potential. Getting the idea? Right? So that's why the dependence of stopping potential on frequency. We also understood that intensity, saturation current increases by the same factor. This is clearly understandable, right? If current is double, if intensity is double, then double number of photons are coming, right? Okay, double number of photons are coming, which means double number of photoelectrons emitted, twice the photocurrent, right? So you can note this down. Okay. Intensity is same, double effect. Intensity is doubled, voltage is 0, double effect. You can check out the graphs. Every point is double in that case. They do strike the metal surface. Just a second. Repeat the question, please. I was unable to understand your question. You are saying that let's say the voltage is 0, right? Okay, and the intensity is doubled, right? So in that case, just try to think about the distribution, right? The electrons with 0 kinetic energy would be double. The electrons with maximum kinetic energy would again be doubled. Every number, every range, in that range, every type of electron would be double of the previous value. So obviously the number of electrons going straight into the anode would also be doubled. Double the current. हाँ देखो स्टैटिस्टिकली सोचो ना, अगर तुमने वोल्टेज यहाँ अप्लाई ही नहीं की है तो let us assume only 3% go straight. Earlier there were 100 photoelectrons, 3 were going straight. Now there are 200 electrons, 6 would go straight. Same statistical factor. कुछ पूछ रहा कोई? If we increase the current, then what will be effect on frequency of photon? How is it possible? Huh? How is it possible? It's vice versa. You know, you frequency of you increase the frequency of photon, then some effect on current, or maybe not. Frequency is the cause, while current is the effect. If you change the effect, how can you change the effect without changing the cause? So I am unable to understand the question actually. Please write the question in correct form. Now, if you are asking this, that what happens if we increase energy of photon? Let's say we increase the energy of photon, okay? Energy of photon, but the number of photons remains same. Okay, I am assuming that the number of photons or the intensity is same. So what happens if photons are energetic? The electrons that come out would also be energetic. Right? Would have higher kinetic energy, but the number of electrons emitted would still be same, right? So it doesn't matter actually. If you increase frequency, the photocurrent would still remain same. Okay, that was indicated by this graph. If the intensity was same, the saturation current was same, right? This small difference for values was because the small difference of values was because when voltage was 0, basically when voltage was 0, so in case of energetic photons, the electrons move quicker, so some time advancement is there. Okay, just imagine the case that the photons are more energetic, so the electrons would have higher kinetic energy, they would move faster, so they would take lesser time to travel. So that's why same charge flowing but slightly lesser time. That's why it appears that the current has increased slightly. It is not because of charge addition, it is because of reduction in the time. But as you increase the voltage in the positive direction, so in every case what happens, the electrons speed up. In every case the electrons speed up and they reach at almost the same time. They take almost the same time to travel if you increase the voltage. That's it. Okay, so this was photoelectric effect, and I would draw one more curve, one or two more curve. See the kinetic energy versus the number of electrons. Okay, it shows this kind of variation. Very few electrons with high kinetic energy, most of the electrons would have mid-range kinetic energy, right? This can be understood. Okay, one or two more things. You see the equation was this: maximum kinetic energy is h nu minus phi naught hc by lambda or h nu. This is an equation of form this, right? This is an equation of form y is equal to mx plus c, right? The slope is positive, right? While the y-intercept is negative. So if I draw this, you get on the y-axis it is k max, on the x-axis it is frequency. Okay, right? You can understand when h nu is equal to phi naught, or frequency is phi naught by h. When frequency is phi naught by h, which is work function by h, the k max is 0, right? So the graph starts from this value. This frequency is called threshold frequency. Remember what is threshold frequency? The energy at which the frequency at which photoelectric effect just happens. Just happens means the electrons would come out with zero energy. Okay. So zero energy is h nu threshold minus phi naught. You can check that h nu threshold is equal to phi naught, right? So this is the frequency is threshold. From this point the graph starts and it's a positive slope line. M is equal to h. Since the slope is constant for any type of metal, the graph for metal 2 would be this, for metal 3 would be this. This is threshold frequency for metal 1, for 2 and so on. If you extend it in the negative direction, this point is minus phi naught. Okay, it is extended. The graph cannot be drawn below x-axis because kinetic energy can never be negative. Below x-axis kinetic energy is negative, right? Which is impossible. So it is extended, it is not drawn. It is extended just to show that the intercept is negative. Okay, shall I erase this? कर दूं अभी? Now another format. This was EVS is equal to h nu minus phi naught. Vs is equal to h by E nu minus phi naught by E. Mostly the the work function is given in electron volts. So electron volt by electron would actually give you a quantity in volts, right? Just for your understanding. Sorry. So even this is an equation of form y is equal to mx plus c. The slope is different, the intercept is different, but this is also an equation of the same format. The slope here would be h by E, again universal constant. So same slope for all the metals. The y-intercept would be this, minus phi naught by E. Is it okay? This comes handy in identifying the values of threshold frequency and the stopping potential. Okay, this is metal 1, 2, 3. करें? Shall we continue? Erase करूं अभी? You know, the beauty of photoelectric effect is the ease is that it has only two equations. The one is k max is equal to h nu minus, okay, phi naught, and the other one is that h nu threshold is equal to wave is equal to work function. That's it. Bas. Every question can be dealt using this. There may be some add-ons. We would do the add-ons as well while doing the questions. क्या? इसमें practical life में हाँ मतलब actually you know there are some light sensors वो सब होता ना in the movies you have seen that laser is incident from this point to this point, somebody cuts, alarm goes off, alarm goes on, right? That kind of thing. It's based on photoelectric effect. It works in dark, absolute dark, okay, till the time the beam is incident on the photoelectric metal, electrons are ejected, right? And as soon as the light is cut, what happens? Alarm. It is used. It is not used for production of current because the current produced is very low. Okay, in microamperes, not useful, right? So the question is, in an experiment, what happens? The wavelength of light emitted is 1.98 into 10 raised to power minus 7 meter, right? In an experiment, this is the wavelength of light emitted, while the work function is 2.5 electron volt. While the work function, somebody is asking, sir, how does photocell and street light work? Array, street light is a different thing, photocell is a different thing. Okay? Photocell is one thing which absorbs light, produces current. Street light, in street light is like in most of the cases it's sodium lamp. So how it works actually, there is a filament which produces heat, okay? When it gets heated up enough, so what happens? The sodium coated on the filament, it starts releasing yellow light, reaches the excited state and comes down, okay? That's the sodium lamp, the street light, right? They are two different things. So what happens? The wavelength and the work function are given. You need to find the K max and lambda TH, threshold wavelength. Just find threshold frequency. चलो यही कर लो, lambda TH. It's a direct question. Correct? This is a very easy question. The energy of the photon is this 12400 by 1980 angstrom. This is EV angstrom. यही होगा or am I making a mistake? So how much? 6.2? 200. If we take 2, no, if we take approximately 200, it would be 1240 by 200, right? है ना? अच्छा 6.2 ही आया है approximately, ठीक है. Approximately 6.2 is the energy of photon, out of which this much is spent. So maximum kinetic energy would be 3.7 electron volts, slightly more than 3.7 electron volts, right? While the lambda threshold, to find lambda threshold, you know hc by lambda is phi naught. For threshold, this is this. So hc is 12400 eV angstrom upon this is 2.5, this is lambda threshold. Okay, EV cancels, this is in angstrom. So the value would be, how much would be the value? 4960, somewhere around 5000 angstrom, right? 4960 angstrom, right? Okay, somewhere around 5000 angstrom. Okay, in most of these questions, you know, if the options are far away, you can use approximations. If they are not, please handle with care, right? Can I raise this? This was an easy one. Let's discuss another. So it says two wavelengths are incident. Two wavelengths are incident. First one is 3500 angstrom and the second one is 5400 angstrom are incident on a metal. Okay. And it was found that in this case, let's say the velocity of electrons was v1, in this case it was v2. The condition was that v1 is 2v2, right? Two wavelengths, two different lights of wavelength, given wavelength are incident on a metal. The electron speeds are in this ratio. Okay, electron speed in the first case is double that of the second case, right? So you need to find what is the threshold, what is the work function, okay, what is the threshold wavelength, both of them. करें? Shall we start? Shall we start? चलो देखो. For the first case, kinetic energy is, you can check, since the speeds are double, the kinetic energies should have a ratio of 4. Okay, so for first case, hc by lambda 1 minus phi naught. For second case, k2 is hc by lambda 2 minus phi naught. This is 4. The ratio is 4. Okay, so you need to solve this only. Hc by lambda 1 minus phi naught is equal to 4 hc by lambda 2 minus 4 phi naught. So swap 3 phi naught is equal to 4 hc by lambda 2 minus hc by lambda 1. Okay. Okay. From here we can calculate. So I'll erase the top part. Three phi naught is equal to 12400, 4 times 12400 by 5400 minus 12400 by 3500. Okay, and you need to take 1/3 of this thing, right? हो सकता है? Can you find it? Approximate values would be these, right? So the answer would be how much? Huh? Somewhere around 5.3, 5.4. इतना टाइम लगेगा? Okay, 1/3 of it. 1/3 of it, right? ठीक है. Let's start with another one. One question involving the saturation current. a beam consisting of wavelengths 4000 angstrom, 4800 angstrom, right, 6000, take 5, take this as 5000, 5000 angstrom, 6000 angstrom and 7000 angstrom is incident on a metal of work function how much, 1.9 electron volt. ठीक है, if area of plate is 10 raised to power minus 4 meter square and intensity of each wavelength is 1.5 into 10 raised to power minus 3 watt per meter square, comma, find the photocurrent ठीक है, assume only 1% assume only 1% ejection rate of the electrons. What it means, that out of 100 photons only one would actually be able to eject electron, right? Okay, okay, what happens actually, 4 wavelengths are incident, this is the work function given and the area and the intensity, okay, intensity is given and 1% ejection. What happens actually, you need to check whether each of them would be able to cause photoelectric effect, okay, okay, then you need to find the number of photons, you need to find the number of photons for each of the wavelengths. Okay, you know the energy of one photon, you know the intensity, you need to find the link between them, right, number of photons for each case. Then let's say for this you get, for 4000 you get 100 electrons, 100 photons, so you would say that only one electron would be emitted and so on. So total number of electrons would give you, you know, from each case you need to find the number of electrons, you get total number of electrons, and for photocurrent you need to multiply the number of electrons with the charge of one electron. It's a long question, right? चलो कर सकते हैं. I'll write the important values. The wavelengths are 4000, 5000, 6000 and 7000, right? So the energy for each case would be hc by lambda, which is 12400 by 4000, which is 3.1 electron volt. Definitely it would be able to. For E2 it is 12400 by 5000, it is 2.48 electron volt. Definitely. E3 is 12400 by 6000, this is 2.06 electron volt. Definitely yes. E4 is 12400 by 7000, this is 1.77 electron volt. No, this won't be able to cause the photoelectric effect, right? This is energy of one photon. Now you know how to check out. We yesterday were doing something of this type. The energy of one photon was h c by lambda. Number of photons was what? Total energy incident upon energy of one photon, right? And total energy was what? Intensity into area, है ना? Intensity into area. Okay, this is the number of photons incident in 1 second. So for first one, the number of photons would be how much? Would be how much? The intensity is 1.5 into 10 raised to power minus 3 into the area is 10 raised to power how much? कितना दिया था? Minus 4. Minus 4 upon the energy is 3.1 into 1.6 into 10 raised to power minus 19. Okay. You know the questions of modern physics of these three chapters, dual nature, atoms and nuclei, would be calculation intensive. They would require you to calculate a lot. So please be ready with that. Okay. How much would be this value? कितना होगा? This would be somewhere around 0.3 into 10 raised to power 12. Okay, 3 into 10 raised to power 11 electrons per second. Sorry, photons per second. Right? But only 1% electrons are emitted. Only 1% electrons are emitted. So the number of electrons for first case would be 3 into 10 raised to power 9 electrons per second. This is N1. Similarly, N2 would be how much? It would be again 1.5 into 10 raised to power minus 7 upon 2.48 into 1.6 into 10 raised to power minus 19. Right? Okay. How to go for this? 6 into 10 raised to power 11 photons per second. As I said, you can use approximation. Just think that this is 2.5. 2.5 into 1.6. How much is that? 400. 4. मतलब somewhere around 4. Right? 1.6. This would be somewhere around 4. If this is 4, this is not 6. अच्छा 1.6 आप करना ही मैं भूल गई multiply. Okay, so it would be somewhere around 4, slightly less than 4. 3.75 into 10 raised to power 11. Right? So the number of electrons emitted would be 1% of this into 10 raised to power 9 photons electrons per second. Right? For the third case, number of photons would be 1.5 into 10 raised to power minus 7 upon 2.06 into 1.6 into 10 raised to power minus 19. So this is how much? This is how much? 4 point something कितना होगा? 0.6, 4 point something. Check out. You also maybe forgot to multiply 1.6 in the denominator. The denominator would be somewhere around 3.2. So 1.5 by 3.2. Okay. It would be slightly lesser than 5. Right? 2. This is यार ये बहुत ज़्यादा approximation कर दिया तुमने. 1.5 को 2 मानना is like huge amount of approximation. थोड़ा चलता है. I am ignoring this 6 only. Rest I am doing. I am calculating here in my mind. Okay. So this one is 4. It would be somewhere around 4.7 into 10 raised to power 11 photons per second, or 4.7 into 10 raised to power 9 electrons per second. Right? Is it okay? So the total number of electrons, you can add them up and find. Let's say n is the total number of electrons. So the photocurrent would be n into charge of electron. Right? Okay. Actually what you could have done, what we could have done, instead of dividing the charge of electron everywhere, we could have just found the photocurrent because of first radiation. So remove this. This is the photocurrent because of first radiation. Photocurrent because of the second radiation. Second wavelength because of the third wavelength. Directly go like this and add them up. Okay. And you can check, this would be a value in the terms of the order 10 raised to minus 7. As I said, it is of the order microamperes, right? So you can go like this as well. So this was a lengthy question, right? Shall I raise it? One last question before we go over to de Broglie. Now the arrangement is like this. Okay, this is the cathode while this is the anode. You have to ignore gravity. Okay, ignore gravity. पहले से ही कहता हूँ. Ignore gravity. What happens? Light is incident on this. The wavelength of light ranges from 400 nanometer to 600 nanometer. The work function of the metal is 2.4 electron volts. Work function of the metal is 2.4 electron volts. Right? What happens? The electrons are emitted. Now this region between the two plates is filled with magnetic field. The separation between these two regions is 10 centimeter. Separation between these two is 10 centimeter. So what happens? Electrons are emitted like this. You need to find what is the value, the minimum value of B. What should be the minimum value of B, so that no photo electron reaches anode. ठीक है, so that no photoelectron reaches anode. Getting the idea? Okay. What happens? Because of magnetic field, the electrons take a circle, and the radius of the circle should be how much? Less than 10 centimeter, right? You remember this? Radius should be less than 10 centimeter, or rather 0.1 meter, less than equal to. How much? How we used to calculate the radius? mv square by r is equal to qvb. Okay, so radius was mv by qb, right? So this mv by qb is less than equal to 0.1. Mass of electron, this is the v, velocity of electron, right? Okay, mv is the momentum. You can instead write it in the form under root 2 mk by qb, right? Can we write momentum as under root 2 mk? Okay, right? So for k, you know, if you can turn the fastest electron in the right time, you can turn all of them, and the fastest electron is emitted by this radiation, 400 nanometer, not by 600. Lower the wavelength, higher is the energy, right? So the fastest electron emitted is hc by lambda minus phi naught. Somebody asked. So this is 12400 by lambda is 4000 actually. It's in nanometer, so we take it in angstrom, right? Minus how much it was? 2.4. Work function was 2.4. This would be 3.1. 3.1 minus 2.4, yani 0.9 electron volt. Please note this is the energy in electron volts, where here you are handling standard units. Sorry, 0.77, right? So this would be root 2 into mass is 9.1 into 10 raised to power minus 31. Okay, the kinetic energy would be 0.7 into 1.6 into 10 raised to power minus 19 upon the charge on electron is 1.6 into 10 raised to power minus 19 into B is less than equal to 0.1 meter. You can find B from here, right? So the questions for this chapter are hardly standalone questions. They are always clubbed with other concepts, like this one was. Okay, like this one was. There are other questions as well, in which photoelectric effect is clubbed with the electrostatic field, that electric field wala concept. Okay, please note this down. Okay, somebody asked, please explain again. हाँ, ये हो गया. Actually बीच में मार्कर भी फेड हो गया था ना. Shall I erase it? So here we discussed particle nature of light. Now we would discuss matter waves, the wave nature of matter, right? Okay, and in which, you know, de Broglie's hypothesis comes in picture. Right? So, okay, de Broglie hypothesis comes in picture, right? Okay, so what happens actually? What he said that nature loves symmetry. This was his statement. Nature loves symmetry. If light or radiation can behave like particles, then particles also can behave like wave. Okay, if wave can behave like a particle, then particle can also behave like a wave. So he said that matter exists in the form of particles as well as in the form of waves. Okay, the wavelength of these waves was given by h by p, where p is the momentum, which is h by mv, which is h by under root 2 mk, which is if it is a charged particle and accelerated through charged particle, if it a charged particle of charge q and it is accelerated through potential difference v, then it is under root 2m qv. Okay, let's say this is the charged particle, mass m, charge q, and it is accelerated through potential difference v. So here the kinetic energy is actually qv. Kinetic energy is equal to work done, right? And you know how momentum is converted into this form? Momentum is mv written as in fact I would rather use kinetic energy, half mv square, it is written as m square v square by 2m, which is momentum square. So kinetic energy is p square by 2m, which means momentum can be written as p is 2mk under root. Okay. Shall I erase this? The last topic is Davison-Germer experiment. Okay, the Davison-Germer experiment, it actually proved that actually matter waves exist, electron waves would actually exist. Okay, so the setup was, there was a filament, tungsten filament, on which barium oxide was coated. Barium oxide was coated. Okay, so that actually it ejects electrons. So electrons were ejected from here. Here was a device called collimator, whose purpose is to produce a narrow beam of electrons. It was incident on a metal target. Okay, this is a nickel target, right? It was incident here, and okay, this is a circular detector. What was done? That actually electrons were incident onto a nickel target, nickel, okay, onto a nickel target. So this this circular detector, this moving detector was actually placed at different positions to find the intensity of electrons, the number of electrons coming. This was connected to a microammeter, okay, okay, more the number of electrons, more is the current, okay. So what they actually did, they accelerated the electrons. The electrons were produced with negligible energy. The V voltage which was applied in this duration, this V voltage was varied from 44 volt to 56 volt, okay, 44 volt to 56 volt, okay. At different voltages the experiments were done. So what they found, that at V is equal to 50 volt and at V is equal to 50 volt and theta angle, theta as 54 volt, a very sharp current was observed, right. Current was high current was observed through the detector, which means a lot of electrons are coming this way, a lot of electrons are coming this way, okay. So what they said, that actually nickel crystals, they have different layers like this, nickel crystals have different layers like this, okay. So what actually happens, these layers, these different layers, these layers diffract the electrons, because between two atoms there are small spaces through which electrons can pass, but they would get diffracted. So between these layers diffraction of electrons happens, okay. And as you know, the diffraction in the diffraction procedure, that a sharp central peak is observed, that sharp central peak is observed at this scenario, right, okay. This sharp central peak is observed at this scenario. So when this is the angle, a central maxima of diffraction pattern is formed. From this, they knew the angle which the layers, the different layers of nickel crystal were making. So from that angle they were able to calculate. You remember that for diffraction it was, the angle was lambda by b, lambda by a was the separation, okay, okay. This they considered as the separation between two layers, okay. So from this, actually from the angle, they were able to find the wavelength which was found to be 0.166 nanometer, okay. While through de Broglie hypothesis, the wavelength was h upon under root 2 m ev, which was under root, you can use this for electrons. For electrons, m and e are constant. This comes handy, 1.22 v, while this is in nanometers, okay. In fact, h is also a constant. This is like this, sorry, this is like this, 1.22 upon root v nanometer, mixed to the formula, right. All the constants are placed. So for v, the value was 0.167, which is like in excellent coordination with the value observed experimentally. So they verified this. Is it okay? They verified this. Okay. Shall we do a question? The question says the de Broglie wavelength of an electron is equal to that of a photon. ठीक है? If v velocity of electron is 1.5 into 10 raised to power 8 meter per second, now find ratio of Ke of electron to energy of photon. Yeah? 10 is for 8, half of the speed of light. तेज चल रहा है काफी. The wavelength is equal, right? So for electron it is h by p, while for photon it is c by नहीं ठीक है, it's okay. Okay, so this is h by mv. You can find the value of lambda actually, right? You can find the value of lambda from here, 6.63 into 10 raised to power minus 34 upon 9.1 into 10 raised to power minus 31 into v is 1.5 into 10 raised to power minus 10 raised to power 8, sorry, not negative, it's 10 raised to power 8, right? Okay. Now you need to find the ratio of kinetic energy, right? Okay. The kinetic energy would be half mv square and the energy of photon would be hc by lambda, h nu or hc by lambda, right? This is half mv square by hc by lambda can be replaced with the wavelength of electron. So this would be h upon mv, right? Okay. It would be half mv square by c into mv. Okay. And in fact you need not solve lambda as well, right? This is v by 2 upon c. V is 1.5 into 10 raised to power 8 upon 2 into 3 into 10 raised to power 8. This is, the ratio is 1 by 4. Right? Okay? Right? Since the de Broglie wavelength is same, we replaced the wavelength of photon with the de Broglie wavelength of electron, right? Okay? And out of which things, some things were cancelled. So very less, values were actually needed finally. Is it okay? Okay, and the time's up. Actually, I just wanted to tell you one thing, one, verbal concept. Let's say two subatomic particles collide. Okay, one neutron and let's say one proton, one electron, they collide. Okay, right? So the question asks, or rather this, let's say there is a neutron. Okay, it's stationary. Now what happens? A proton and an electron, they eject out in opposite directions. Okay, so the question asks, what are their de Broglie wavelengths, right? You need to remember this, their de Broglie wavelengths would be same because they would carry same momentum in opposite directions, right? Okay, so wherever this de Broglie thing comes in picture, okay, any collision or something else can be put into place. In collisions, momentum was conserved, it was all about momentum. Okay, any of that can be picked and placed into de Broglie. A question can be framed mixing these two concepts, right? So expect questions of mixed variety rather than a question of standalone type, standalone de Broglie. It won't be asked, it straightforward. So that's all from my side. Thank you.